A landscape designer plans to construct a rectangular garden whose area is 2,000 square meters. One side will consist of a wrought iron fence, which costs $90 per meter. The remaining 3 sides will be constructed from chain link fence, costing $25 per meter. Determine a function for the total cost of the garden, where X is the length of the wrought iron fence in meters. So it's a rectangular fence. So it's always good to draw a picture. And it doesn't really matter which side you label as X or Y for this problem. So here's X and here's Y. So we want X to be the wrought iron fence. So this side is going to cost $90 per meter. And the remaining 3 sides are going to cost $25 per meter. The constraint equation we were given was that the area of the garden must be 2,000 square meters. So the area of this garden is going to be X times Y, and that must be 2,000. We want our cost function to be a function of X, so that means if we want X to be left in the equation, we should actually solve the constraint for the opposite variable. So Y will be 2,000 divided by X. So my cost function will be the price of each side times the length. So this is in meters, this is $90 per meter. The meters will cancel and it will come out in dollars. So we're going to have 90x plus 25y, but we want y as a function of x, so it's 25 times 2,000 over x, plus this side is also length x, 25x, plus another side that is 25y, so it's 25 times 2,000 over x. So this is your cost function, and you're good to go for this part. Part B says, well, what dimensions of the garden will minimize cost? So this is really important. The final answer wants the dimensions of the garden, so that's going to be returning both x and y. So I like to write that down so I don't forget when I'm done with all my math that I need to make sure that I report back the dimensions of the garden. Okay? And so I'm even going to write here, that's x and y. So we're going to work in variable x to solve the problem, but we want to make sure we return the right information at the end of the problem. So the domain of this function is going to be required because we need to know what values of x are in play. So if you look at your constraint equation that we created back in part A, the constraint says the garden can be any dimensions that we want as long as when you multiply x and y together you get 2,000. So this equation right here is what you want to do your domain check on. And the domain of this function is going to be 0 to infinity. We cannot include 0 because if you include 0, you'll get 0 in the denominator here, which isn't allowed. But if you back that up, if you have 0 here, this whole left side of the equation is 0, and that cannot equal 2,000. So this garden has to exist. So we can't include 0. But if we let y go to 0 or get really, really small without actually getting there, we'll see that the value of x is going to blow up to infinity. So 0 to infinity is the appropriate domain for this function. The next thing I need to do is I need to find some critical values. So before I find some critical values, I'm going to clean up this function just a little bit to make my derivative easier. So c of x, if we add 90 plus 25, 90x plus 25x, we get 115x. And then I've got a 25 times 2,000 over x and another 25 times 2,000 over x. So that's actually going to give me 50 times 2,000 over x. over x. For the derivative step, it might be a little bit easier for me if I use negative exponents, so I can use the power rule to take the derivative. So 50 times 2,000 is 100,000 x to the negative 1. So now I'm going to take the derivative of this function, and I get 115 minus 100,000 times x to the negative 2. But in order to set this equal to 0 and solve, remember that calculus is easier with the negative exponents, but algebra is easier if you use positive exponents. So I'm going to rewrite this as 115 minus 100,000 over x squared, and I want to set this equal to 0. So I get 115 equals 100,000 over x squared. X squared equals 100,000 divided by 15. This will reduce, divided by 115. This will reduce to 20,000 divided by 23. So technically, when I take the square root of both sides, I get two values, plus or minus the square root of that. But our domain says x can never be negative, so I'm really just going to keep the positive case. This will reduce down to 100 times 2 root 23. So I know my critical value, but I have to figure out what type of value is this. Is this a relative maximum or is this a relative minimum? And the goal here is to minimize the cost. So you have two options here. You can use the first derivative test or you can use the second derivative test. The way you decide, both will work, but the way you usually decide on which path you want to go down is look at the derivative step, okay? What type of function were you looking at? So by rewriting my original function like this and using the power rule, the derivative here came back as another function that I could use the power rule on. So if I were to take the second derivative of this function, then the derivative would be really easy to take. It would actually kind of get a little bit simpler and easier for me to plug values in. If I were to try to plug numbers into the first derivative, it would also work, but it might be a little bit more complicated. So I'm going to do the second derivative test. I'm then going to show you at the end of the problem what the first derivative test would have looked like. So for the second derivative test, I calculate the second derivative. So the derivative of 115 is 0. The derivative of this, it's going to be negative 2 times negative 1 times 100,000. So I get positive 200,000 x to the negative 3, which is 200,000 over x cubed. When I plug my critical value into this, I end up getting 200,000 divided by 100 over 2 root 23 cubed. We can see by just looking at this number, I don't really care about the value of the number. What I care about is the sign of the number. The numerator's positive, the denominator's positive. This is a positive value, so that means that the function will be concave up here. So this is telling me that this is a relative minimum. So I do in fact have a minimum. Now, this is a great thing to be able to cite because we also then have to verify that it's an absolute extrema. So we have to make sure that we now know this is an absolute minimum. So one way you could do this is you could look at limits and test the end behavior of the original function. That can get quite complex, but there's a caveat that we've learned hopefully in class that said since there is exactly one critical value on our domain of 0 to infinity, then x equals 100 times the square root of 2 over 23 must be an absolute extrema. So be very, very careful if you cite this. This says that if there's exactly one critical value on your domain for your function, this is why the domain is so important, then that critical value is an absolute extrema, but it does not specify what type of extrema that you found. So you have to use, if your domain is open, you have to use either the first or second derivative test to determine what type of extrema you have to then make this statement. So it is then implied that this absolute extrema is an absolute minimum because it was a relative minimum. So now that I've found my critical value, I've verified what type of extrema, and I've now verified that it is an absolute minimum, I can now report back my final answers. So the goal was to give the dimensions of the garden. So the dimensions of the garden, oops, can't spell garden today, are x equals 100 times the square root of 2 over 23. And to get the y value, I go all the way back up here to my constraint and see where we solved it for y. That's the easiest place to plug it in. So it was 2,000 over 100 times the square root of 2 root 23. We need to include units, and you're done. I know it's very tempting to get decimal places, but we are perfectly happy with exact answers. You do not have to simplify this any further. And just to be clear, in case anyone's keeping track when I'm putting the topics down, this was an optimization problem. So it's not a bad idea when you're running through these problems on these practice finals or these former finals that you're maybe somewhere on the paper calling out what the topic is, and that way you can kind of organize the problems by topic.